Neil Friedman is visiting Israel from the US and has found the time to come and speak at our meetup. So please, give him a hand. After completing a PhD in physics, Neil started working in C++ doing low latency, high frequency trading. He's interested in the challenges of writing robust code at scale and highly configurable code that minimizes performance trade-off. Thank you.
Thank you. Hey everyone. So, title of my talk, Understanding Optimizers, Helping the Compiler Help You. So, that's really indeed what this talk is about. So, a lot of people have there's a sort of viewpoint towards optimization which is very bifurcated, which is like, the compiler is really smart, I'm going to write some code, I'm going to let the compiler do some optimization, and then like if it's not good enough, then I'm going to like crack out some assembly and I'm going to write all my own assembly, and that's like this or that. And I don't think this is a good viewpoint, because a lot of times you can do better if you help the optimizer instead of going to one extreme or the other. And that's what a lot of this talk is going to be, just being able to understand what the optimizer is doing, why, and how you can help it do what it needs to do. Soon as. Okay. So what the talk is, I guess I already said a bit of that, but getting a better feel for the assembly the compiler produces. What optimizations you can count on a production-grade compiler to do for you. This is actually very important. Constraints on the compiler. There's some things that I'm going to show you where you're like, why can't the compiler do this? And you'll be really annoyed to see the compiler is actually not allowed to do it. Some things which limit the compiler doesn't know certain things like runtime information, and it also doesn't know what you care about. And I'll talk about that as well. Some things the talk is definitely not about. So the first thing is a hardcore tutorial on assembly. I'm definitely not qualified to give that talk. I'm not an expert at assembly in any way, shape, or form. Talk's not about benchmarking. I'm not going to be talking about benchmarks. Code that's not there was always faster, and that's most of the idea behind the talk. More so than very specific claims about performance. There's nothing about multi-threading here. Everything here should be assumed to be single-threaded. Multi-threading obviously can be really important for performance depending on your domain, but it's such a huge topic. There's no way I can really talk about it and talk about other things. I'm also not really going to talk about, I'm not going to talk at all about LTO, link time optimization. The linker can be more intelligent than the compiler because it has access to more things. Again, it's just not something that I'm really expert enough in, and a lot of the times the compiler's optimizations are still really critical because the compiler, unlike the linker, is parallelizable, so it gets to spend a lot more time doing optimizations on a given piece of code than the linker does. By the way, I know speaking English, people here speak English, but if you feel like you don't understand something that I said or a word that I used, feel free to stop me. I would try to give it in Hebrew if my Hebrew was good enough, but it's not. Okay, so why do I think it's even important to understand the assembly that comes out? I mean, why not just write whatever and just measure, and then just write something else and then measure? So, I mean, first of all, obviously this is not a very good way to go about things. This is kind of like a random walk. You just bump from one set of C++ code to another. It's going to take you a while to arrive at something fast. There's also other things. Measurement's not a simple silver bullet. First of all, if you're not the end user of your code, you don't have access to your end user's use cases. And even at a company, I mean, it's very common that your job in the company is to maintain some library that someone else uses. And they may give you some access to their use case, they may give you a lot, they may give you a little. In HFT where I work, they give you basically none. So I used to be a library writer at HFT, now I'm on a trading team, and this is a real issue. And the other thing is that it can cost a lot of man hours to make changes based on writing first and then measure it. I mean, when you create a library or a piece of code, you make a lot of decisions. And if you don't know anything about how assembly is generated, you may find out that some of your decisions, it's hard to undo them. You're going to have to basically change a design decision because the performance can't be worked around the design choice. And that can be expensive. So a little bit about myself. So I work in high frequency trading, HFT, at a company in New York. So it's very, very, very performance sensitive. People in HFT usually talk about, total latencies of something like microseconds. So every instruction counts. So I work on a small team of developers. There's only 6 people on the team. Only 4 of them are C++ developers at all. And a lot of those people have other responsibilities. So there's really not a lot of man hours to go around, but performance counts a lot, but also things are always changing. So what do? Well, it really, really helps if the code you write the first time is fast. Because sometimes you might say, hey, we should optimize something, and 6 months will go by before you have time to look at it, because that's just life. There are even more important things to do. Okay, so why am I giving this talk? I'm not a compiler developer. I'm not an expert about compilers or on the standard, but I've spent a lot of time writing code, looking at the assembly. How many people here have used Godbolt? Godbolt 2? I just call it Godbolt because I see everyone moving on it. Great. Okay. So it's a website where you can easily look at assembly from code. Okay, so I'd like to start with a motivating example. This actually came up literally a few weeks ago in code review. So we were talking about using a vector for something. It was a vector int. We wanted to use clear. Now, if you look at the documentation, so what clear does is it removes all the elements from the vector. Okay, sets the size to 0. So the question came up, okay, well, the documentation just says this is on. It has to delete all the elements, okay? So, it came up, okay, so is this actually on for a vector int specifically, right? If you know that it's integers like a very simple type, do you expect it to still be on, or do you expect this to get optimized? So let's have a show of hands. How many people think it's still on for vector int? How many people think it's O1? How many people think it's O1 because standard library implementers are smart and would have made sure to write the code so that it could be optimized this way?
Depend which standard libraries. Not all of them are equal.
That's true. When I talk about compilers and standard libraries, I'm really only talking about the big 3, plus maybe ICC, which doesn't have its own standard library. But yeah, those compilers are generally, the people working there know their stuff very, very well. So, okay, we're going to come back to this example. Okay, another example, a saga of sorting. So this is how a lot of C++ developers, in my experience, transverse through their beliefs about sorting speed. So beginners, they know from school that qsort and stdsort are probably both quicksort implementations. They're both n-log-n. They're probably about the same. Then they start learning. They read Scott Meyer's Effective STL, and they learn that stdsort is faster. This is actually pretty much true. But then they transition to being expert beginners, and that's not a compliment. And then they just say, well, the compiler is smart. My function pointer will get inlined because magic, and then it'll be about the same speed. And then hopefully you don't get stuck there. You continue, and you're like, well, hold on. It's not always so simple to inline a function pointer. Okay, so here's a poll for the audience. So here's a comparator, bool, mycomp. Maybe it's a little too obvious after what I just said, but so here's 2 calls to stdsort. So the calls are basically the same, but I've done something a little weird with the second one, which is I just wrapped my function in a lambda, and I'm passing the lambda which calls the function to stdsort. Why would I do such a thing? I don't know, it's pretty weird. But who thinks that the performance will be the same? Raise your hands. Who thinks that the first one will be faster? Who thinks that the second one will be faster? So we get a variety of opinions, which is good. So, okay, how do we resolve this? You could benchmark, but when you're making very precise claims about 2 bits of code that you expect to have like almost exactly the same assembly, even if you're not an expert, it's not terribly complicated to just get in there and look at the actual assembly line by line by line. And that's what I did. Okay, so we're getting the secret from the machine itself, so to speak. Okay, so if you look at the assembly, you write out like a simple function foo that takes a vector and tries to sort it. You know, we'd like to see if the comparator is inline in both cases. And how do you do that? Well, okay, here's the assembly. There's like a whole bunch of push instructions, which is basically setting things up on the stack to call arguments of the function. Then it's going to call this function std intro sort loop. This is like the blood and guts of the quick sort function. It's a recursive function. Intro sort is a hybrid sort between quick and heap sort. And deep inside the bowels of this intro sort function, you will find assembly that looks like this. Okay, so it moves a few things. These are probably maybe loading up function arguments. And then it does, actually that's definitely what it is. And then it does call R12. So the call instruction in assembly calls a function. And R12 is a register. So this is telling you that it's doing an indirect call. The compiler is calling some function that it doesn't know. And that means that, in this case, it was not inline. And if you go and look at the assembly for both of these, you'll actually find that the version that uses the function pointer directly does not get inline. But the version with the lambda does. And actually, the version with the lambda will run faster. And this is really bizarre in a way, right? And the reason why it's bizarre is because, look, this one has more code, not less code. I mean, surely like a lambda is another hoop to jump through, right? So maybe that hoop doesn't cost anything, but how can that hoop have negative cost? So hopefully during the course of this talk, I'm going to explain, well, why is this one usually faster than that one? And it won't always be, by the way. GCC on 03 will produce identical assembly for both. That's like one specific compiler and one specific optimization setting. But any other compiler on 02 instead of 03 will not do it. Okay, so some things that you want to think about when you're thinking about what the compiler's perspective looks like. So those of you who have not seen the amazing movie Training Day, you should go do that after this talk. But in it, you have this character who tells his cop partner, it's not what you know, it's what you can prove. And he reiterates this throughout the film. And the compiler is exactly the same way. It doesn't matter what you think the compiler should know or what you know about your code. All that the compiler cares about is what it can prove. When the optimizer runs, it has to produce code that is always correct. Okay? So always means it has to have the same behavior for any set of inputs. And correct is defined by the as-if rule. Has everyone heard of the as-if rule in C++? So basically says when you perform optimization or when you do anything, it has to perform as if you did the unoptimized thing. There can't be an observable difference. So the second thing to think about is basic blocks. So those of you who have taken a compiler course have probably already heard about basic blocks, probably know more about it than I do. But the basic idea is that a basic block is a piece of code where there are no entrances except at the beginning and there's no exits except at the end. Once you start running this code, you're going beginning to end and nothing can jump in the middle either. It's just one contiguous opaque chunk to the compiler. And basic blocks are really nice because inside a basic block, there's very few things that are observable in the middle. I listed a few exceptions there. I already said I'm not going to talk about multi-threading. Volatile is a bit of an edge case for very specific things. And globals are basically death for performance, or they're not good for performance. So, but generally speaking, basic blocks not very observable on the inside. So you're mostly worried about the correctness at the beginning and at the end. And basic blocks are especially important to this talk because the beginning of a function is generally always the beginning of a new basic block. And in most cases, basically anytime you're not using LTO or if you're not using a static function, a compiler doesn't know all the places that a function is called from. It generally has to produce a function that's always correct. And this is actually a really big limitation. So here's like two diagrams of graphs. So once you start thinking in terms of basic blocks, and a basic block can jump to a different basic block, your program can be represented as a graph of nodes. So can anyone guess what does the first one represent in this basic block? Yeah, if else. That's very important. It has the else clause too. Otherwise, there wouldn't be two nodes there in the middle. You just have the arrow cutting from the first to the third. How about B? What kind of loop? of annoying, right? I'm not gonna let you get away with just a loop.
For a while.
Yeah, so it's actually can't be a for loop. And the reason why is because a for loop has some code that it only runs once, right? There is no code on the right that only runs once, right? Because when this loops around, it runs the whole first node again. So a for loop has to have a little block first that runs its own code. And then, yeah. Okay, I'm being a little pedantic right here. Sorry. Okay, so here we could like count basic blocks if we wanted. Maybe in the interest of time, I won't go too much into this, but entering foo, that's one basic block. The setup of the for loop, that's another. You have the body of the for loop, which itself has different blocks, like this region, the if, the call to bar. Okay, another thing to think about when you're dealing with a compiler is information that's static versus information that's dynamic. Static information enters in at compile time, dynamic information enters at runtime. This could be for fundamental reasons, like if it's a command line argument, it's not going to be there at compile time, right? Or it could just be how you wrote the code. So very simple information, very simple example is these two versions of these two different functions. Okay, when you take a vector, the size of the vector is a value, right? You only know it at runtime. You don't know at compile time how big your vectors are. When you deal with an std array, you get a template parameter, which is the size of the array. So you know exactly how big it is. So this kind of illustrates my previous point that types are static, generally speaking. Well, no, not generally, always. Values are dynamic in general. So value versus type. And that's also why one function is a regular function and one is a template, right? It's got to be a template because you could have different types. Okay, so a quick summary. We're constrained basically in these different ways, producing correct code, having a lot of some kinds of information, not having so much of others. One thing to note is, so when compilers try to optimize, they try to make changes that are definitely better. But sometimes it's not possible. So in some cases, they simply make trade-offs. And in other cases, they tend to fall back on producing assembly that is closer in spirit to the original source code. And one example of that, by the way, is I talked about loops. When you have a vector, the compiler doesn't know how big your loop is, right? So how does the compiler decide what kind of code to generate? The answer is that it doesn't use the size of the loop, right? It has to make guesses. So if, for example, you compile with O3, which is common, the compiler will basically just assume that all of your loops are big. And this is a reasonable assumption because if the loop is small, you're not going to spend long in it anyway, right? But it will do things like loop unrolling, which are great for big loops and not so good for small loops. Because if your vector is size 3, you're not going to get any benefit from loop unrolling. You're just going to be working through the edge cases, and you're just going to upload your code for no reason. But the compiler just has to make these choices all the time. So it's not easy to be a compiler, in other words. Okay, so I'm going to go through some examples of different kinds of optimizations that compilers do, a little bit about how they fit in with each other. Hopefully some of these will be fun. So let me start off by talking about inlining. And usually when you talk to people about inlining, the first thing that they'll say is that, or that they think of, is that inlining is really important because of the overhead of calling. You don't have to, load things into registers, things like that. And that's actually not at all true. Actually, people think that a lot as well, by the way, in the context of virtual functions. People will be like, well, virtual functions are bad because of this overhead of calling the virtual function. Of course, there's truth there, but really what's so big about inlining is that the compiler's ability to analyze your code when something is inlined is so much greater. There are so many optimizations that can only be done when a function is inlined, that's where you derive real benefit. And actually, that's going to be highlighted in the slides to come. So there's two sort of separate considerations in inlining that it really helps to be aware of. So the first is whether the compiler can perform an inline, right? So here we call like a direct versus an indirect call. So you have a virtual function, barring some rare circumstances. or a function pointer, the compiler just cannot know where the function is going. So even if it wants to inline, it can't do it. If it's a direct call, the compiler always has the option to inline, but it may decide not to, usually because the function is just too big. And that's the second bullet point. Does it want to? Generally speaking, the shorter the function, the more likely to be inlined. The overhead will be like a larger fraction, relatively speaking, of the function, and also the amount of code bloat that it causes, right? If the function is shorter than the number of instructions required to load the registers up to call it, then there's no code bloat, right? Then you actually reduce your code size by inlining. So under those circumstances, it's basically guaranteed. There's actually another situation that comes up now a lot in C++11 where inlining is almost guaranteed. Can anyone give another example? Lambda, but why are lambdas so commonly inlined?
Const Impact?
Because the compiler creates them.
Because it's super low.
It's because they're only used once, right? So I said, what's the downside to inlining? The only real downside is bloat, right? Why does bloat happen? If I have a function that's 100 lines long and you inline it 10 times, then now you have 1,000 lines. But a lambda, most lambdas can only be used once because they're temporaries, they get passed around. So if your function is used exactly once, there's no bloat, right? Assuming that it doesn't need to be exposed in the symbol table or whatever. So lambdas almost always get inline in real world use cases. So here's a real simple example of inlining. I have foo, I have bar. You can see in the generated assembly that bar does not actually call foo. For functions like this would be incredibly ridiculous and expensive if bar were actually to call foo. But in my sorting example, of course comparing is only one thing that happens during sorting, but comparing, if you want to sort from in reverse order, checking if x is greater than y, that's just one assembly instruction. So it's also very ridiculous to load up the registers. So actually, with inlining, we can go back already and revisit our previous example, right? So let's say, I want to think about, okay, do I think that vector t is ON or constant, right? And does it require some kind of special implementation? Do they have to do if trivially destructible sort of stuff, right? Okay, well, here's basically what clear looks like, right? So this is a member function. I'm assuming that the vector has pointers called, mbegin and mend, which are exactly what you get from begin and end. So what does it do? It has to loop through and call the destructors, and then it sets the end to the beginning, right? So which sets the size to 0. That's all that clear does. So, okay, well, let's look at this code for a second, right? So tilde t. So t is known statically because it's a vector, it's a template. So for us, this is just exactly int, okay? What is tilde int?
Nothing.
Nothing, right? So when the compiler does this optimization pass, it's going to be tilde int is a function, maybe I should inline it. And then it's going to look inside and see that it's empty. So how likely do you think an empty function is to get inlined?
100%.
100%, okay? But inlining an empty function is actually just deleting the call, right? It's just a no-op. So this is always going to turn into a no-op. And then a loop over nothing, how likely do you think a production-grade compiler is to remove the loop? 100%. Yes, but here it's very easy because it is a local variable.
And the begin and mn is probably primitive pointer or something.
Yes, but they're actually not being, okay, you're saying not equals would,
I mean some copy constructor or whatever.
yes, but that's only executed once. The only thing that has to be executed over and over is plus it,
And
which is local and not equal.
The reference.
And it might have some.
I think
it's
it's
no
local.
proof for.
Right. But But for pointers, it's pretty easy to prove that. So this is what I mean when I say you don't need any kind of special attempt by the library implementer to know that you're just going to get an O1 function for clear. Okay. I want to distinguish the situation from there's a lot of other things. If you call push back on a vector, are you going to get a nice, fast, parallelized memcopy if you have to resize the vector, for int? That's not trivial, right? That depends. Does the compiler do it automatically, yes or no, or maybe, or is the implementation quality such that they hand code that in themselves. You can't assume that unless you've already looked it up for whatever library you use. But this you should be able to assume for any production quality compiler. Okay, so const propagation, my next optimization. It's a very, very famous optimization, one of the first ones that people talk to. If you think about what const propagation is in the context of what I said before, I said that types are static, values are dynamic, right? Well, const propagation is like the $1 million exception to this, right? This is a situation where a value becomes static.
Yeah.
So that means basically that a value which is known at compile time is allowed to influence static code generation. So the specific thing, the specific value of it influences what assembly comes out. It's an incredibly important optimization, and it's actually very heavily intertwined with inlining. I'm going to give an example of that real shortly. Okay, so the most common example for const propagation is arithmetic. If any of you guys saw Matt Godbolt's talk from CVPCon last year, he marched through a whole bunch of crazy arithmetic optimizations. So here is a factorial function. Foo returns, y plus factorial 4, and this was the assembly generated for foo. Okay, so I mean this is child's play for a modern compiler. They can do much crazier things than this, but I mean this is impressive considering that factorial is recursive. Compilers don't deal that well with recursive functions comparatively. But you can see that the 24 just becomes a hard-coded constant in this way, one instruction. Okay, so these optimizations are really cute, but they're very important in certain kinds of code, but much less important in others. So I'd like to take an example of a different kind of const propagation. Okay, so in this type of let's see what's going on. So I wrote my for each, which is kind of like the library function for each, except that it's a lot simpler. It's not a template. And it's mine. That's why, hence mine. I got tired of foo and bar, and I kept using foo twice on the same slide. It was embarrassing. So it takes a vector and a function pointer, and it just applies the function pointer to every single element. And here's foo. This is the function that I'm planning to apply. And this is finally bar. It takes the vector, and it tries to apply my for each to it. Okay? Now, if we think about this function, my for each, right? So in the abstract, my for each cannot inline f, because it doesn't know what f is, right? That's pretty obvious. And a key point here is that it sort of ties together inlining, const propagation, and basic blocks, but you can't const propagate across a function boundary normally, okay? And I know that seems like I'm stating the obvious, but a lot of people will be surprised, like, why doesn't this get inlined? Well, if my for each has to be correct, no matter who calls it, right, then if my for each does not get inlined, then when you call it here, it's just going into this generic implementation of my for each, which has to have an indirect call. So there's no way that bar is not going to have an indirect call, unless
All of it is inlining bar.
unless my for each is inlined into bar.
Yeah.
Yes. So that's the punchline. And this is also why inlining is so important, because it allows other optimizations to take hold, right? Like, what's going to happen now is that my for each will get inlined into bar. Once my for each is inlined into bar, now it's part of the same basic block. So now const propagation says, okay, well, this thing that's called f here, which is a runtime variable, this is really known at compile time to be foo. Foo is like a literal pointer to a function, right? And as soon as I know that, I change this from an indirect call into an inline call. Okay, so this is also const propagation, but it's const propagation which allows inlining. Okay, so you can actually see one of the cool things about inlining is that inlining triggers further inlining. So even if the first layer of inlining seems like a net loss, that can trigger more inlining, which is a big win. So it's kind of like looking at the tree of a game. Like, you might start off a chain of moves by sacrificing something, but down the road it's beneficial. So this is the assembly. Sorry, I can't scroll down that easily, but that's basically all of it. And you can see there's no call instruction anywhere. Okay, so now we're going to talk about passing by reference and how that influences assembly generation. So here's an example, foo, bar. Let's just assume for now that they're not going to get inline, or they're not available for the compiler to see even. They could just be declared, right, and defined elsewhere. So now I have this function called quux. Okay, so I loop over x, which is this vector. I call it bar. And now I do, okay, if Boolean, then foo. So I'm passing bool by reference instead of by value. So if I remove the reference, or if I don't, I get slightly different assembly. Okay? So here's another chance for an audience poll. So this is two different sections of assembly. One comes from the version where the Boolean is passed by reference. The other one comes from the version where the Boolean is passed by value. So let's do an audience poll. So how many think that the first one, that this is passed by reference? Okay. And how many think that this one is passed by reference? Okay, great. So everyone who put up their hand was right. So here, the test is performed on a register. There's no indirection. The value is already loaded up into a register. Here, it's a comparison on via a pointer, okay, which references basically pointers. So this already has some impact on the assembly. But some of you, I mean, you should actually wonder, well, but why, right? Like, I should be able to copy the Boolean into a register at the beginning. And then, when I do this loop, which I could do 1,000,000 times, I'll be doing a more efficient assembly instruction that will do a comparison on a register, right? And in fact, you can do a much more dramatic optimization than this. If you compile this code on O3, what many compilers will do is they will actually do a Boolean pullout, okay? They will pull the Boolean outside of the for loop.
They make two loops.
What's that?
They generate two loops.
Yes, exactly. So first will be the Boolean, and if the Boolean is true, then they'll execute one version of the loop without the Boolean, where foo always gets called. And if the Boolean's false, they'll execute the second version of the loop. Okay?
It could be that the order matters.
The order of what?
You should alternate the calls for bar and foo.
No. It will do them. It will respect the order. I'm saying there's two versions of the loop. The first loop does bar and then foo, and the second loop only does bar, and it will pick which to do. But this will only happen if you pass by value, right? Why does passing by reference screw up everything? Okay, well, remember I said it's not what you know, it's what you can prove. Okay, so here are the things that I am going to call quux with. I'm going to call quux with this global variable called myBool. And bar, unbeknownst to the compiler, bar is this delightful function that flips this global back and forth. Isn't this lovely? So when you call quux, what's actually going to happen is every time you call bar, B is going to flip. So you're going to call foo only on alternating loop iterations. And this is 100% legal usage of quux. There's no undefined behavior here whatsoever. So the compiler says, well, I'm not allowed to generate a program that would produce different output even for the most ridiculous and corner casey inputs, and therefore I can't do it. So when you pass by reference, one thing to think about, one useful takeaway from this is, what if my reference were a global? And what if every single non-inline function that I call touches the global? And that is what the compiler has to deal with. That's what its limitations are in terms of optimization.
What is this const meaning?
What is the const meaning?
Const reference.
It just means that your reference cannot alter the value of the value.
I cannot change it inside, but it can be changed outside.
It can be changed outside. Yeah. And even the first part of what you said is not completely correct, because you have const cast, and const cast is only considered undefined behavior if the original value is const. So if you have a non-const value that gets passed by const reference somewhere, it's 100% legal code for that function to const cast away constness and change the value. That's also legal. So that means that another version of this, another example of this which is similar, is that you can have a function of value that you can have a parameter that you declare locally by value, or was passed to you by value. And you can pass it by const reference somewhere, and the same thing happens. You cannot assume that the value didn't change, even though you passed by const reference. And this is actually very damaging for a lot of optimizations. Okay, so now this is a good segue into talking about what impact const actually has. So as I just said, the impact of const on references is pretty much zero, because you can just cast away const whenever you want. So the only way to prove that it's not legal to cast away const is to see the original value and know that it's const, right? So there's no actual impact of having const on a reference. Only const on a value does anything. So here's an example where const ought to impact. So here I have some function foo. So foo takes by const reference, right? But we know that foo could actually change things, and that's not undefined behavior. So the compiler has to respect the fact that foo could modify its input. Crazy though it seems. So here a bar though creates const int y. Y is equal to x plus 1, foo y. And afterwards I return y plus x. So now it's obvious that if there's no const here, right, then y could change. And then when you return y plus x, it could be anything, right? But it is undefined behavior to change a value that's const. So there's no way that foo is allowed to change y, because the value itself is const. And then we know that the value of y is still x plus 1. Now we just talked about integer overflow. That's also a nice segue for this. So because int is signed and not unsigned, are we allowed to assume that x plus 1 is greater than x?
Yes.
Yes, right? If it was unsigned, we would not be allowed, because it's not undefined behavior to wrap around. But for signed, it is undefined behavior. And this is actually why it's undefined behavior. So you can do optimizations like this. Or one of the reasons why. Huh?
UB never happens.
Yeah, UB never happens. The compiler can always say, if this happens, then it's UB, but I don't care about that happening, so I'm just going to optimize it as if it never happened. And so your compiler should optimize this, right? Like everything I've said is like legal, C++, so the last line should be returned true. Okay, except that it's not. Okay, so even in modern production grade compilers like GCC and Clang, I didn't test MSVC, but they both emit comp here. They don't just return true, even though they could. Why? I don't know. Compilers tend to be very conservative about addresses escaping. So in other words, once someone else can see the address of this variable, the optimizations tend to not happen, even though they really are undefined behavior. I've heard from someone that the idea is being toyed with. The net effect of this, you can see, is that the value of const for optimization is, one person that I know put it this way, it's not 0, but it rounds to 0. So it's basically 0. What would help, there's two things that would help here, right? One is passing by value. That would actually fix the problem. The second thing, well, can someone tell me what it is? Inlining, right? Inlining and passing by value. Inlining and passing by value are the solution to all of our problems. So if foo were inline and it could be shown that in foo's body, it didn't let y's address escape or change it, then we could also perform the optimization. But then we don't need const anymore, because once the compiler can analyze whether y changes, it doesn't need the const annotation. So const turns out to never help us, that I can see. Yes?
Jason Turner did top constant CPP on where constant, like all the code was removed by the compiler.
Const or const expert?
No,
Const.
Okay.
I didn't see
Console.
it was passed for
Again, console.
Okay, I'll look it up. Yeah. Oh, yeah. Please do. I mean, I'm sure there are other examples, but I mean, this is like a very simple one. So, at the very least, like it's nothing to depend on. But yeah.
You mentioned const expert could help here?
Const expert won't help here. Const expert also is not really something that is very relevant to optimization. There are some tricks you can do with const expert. The number one thing I can actually think of as a usage for const expert is if you have a lookup table or if you have a large value that you want to be computed at compile time, the compiler might not want to do that. If it's a small value, you don't need const expert because the compiler will just do it, as you saw with factorial. and it's been doing it for years. If you have like a big lookup table, you could maybe make it const expert and compute it with a const expert function, and that can try to force the compiler to do it at compile time. Other than that, it's, you know, yeah, I don't think so.
Specifically in this function, so why would const export? No way it's going to change, right?
Why is const expert not going to change it?
No way that anybody can change it if y was const export in this situation.
Well, even with its const, nobody can change it, right? And the compiler still doesn't do anything, right? But even if it was const expert, I mean bar, and even if bar was const expert, there would still be int x, which is this runtime variable entering into it. So it's not going to turn it into a compile time computation, right?
I'm not sure it will compile. It would require
Foo to be const expert too.
well, at least x to be const expert to compile. If you
No,
want to measure.
function parameters cannot be const expert.
Hence, y cannot be constant.
No, that's not true. Y can be const expert, but x cannot be const expert.
Calculate y as compile time.
So const expert functions don't have to be used in const expert contexts, but they may be used in const expert contexts. Marking a function const expert says this: if all of the arguments are the results of constant expressions, then the result of the function is a constant expression.
Because y is not a function. So if you const expert y,
Concept
it's
of
not conditional about whether the arguments are.
Oh, baby.
You cannot initialize the
You
function.
can't do the runtime variable. You're right. Because it has to work either way. So yeah. Okay. But anyhow, const expert digression notwithstanding. Okay, let's talk a bit about branches, using and eliminating branches. So, okay, so here's an example. Foo takes an optional int by reference, whatever. It has int y equals 1. If x, it wants to set y to the value, return y. So this is kind of like a value or sort of thing. So, okay, so, you know, personally, like when I first learned about optional, it was like some number of years ago, and at least at the time, I was unhappy that I felt like they made the unsafe thing easy to write, which is star. So star, or dereference, or whatever you want to call it, on an optional performs an unchecked dereference, right? Dot value performs a checked dereference. So this will check if the optional is valid. If the optional is not valid, it throws an exception. And I was like, well, why do we make the unsafe thing really easy to write and the safe thing hard to write? And one, I'm sure there's many other reasons. I'm sure you guys will tell me afterwards. But one of the reasons that I got from people often was that it's slower, right? Because it's a branch. And they were like, well, this is the idiomatic usage of optional, right? You check if it's valid, and then you remove the value from it. So why would you want to have 2 branches instead of 1? And I heard this argument actually from a lot of people, including experienced people. But if you actually bother looking at the assembly, there are not 2 branches, right? There's one comparison, there's move, you know, the value, jump, move, whatever. But there's definitely not 2 branches, right? There's one comparison. So why aren't there 2 branches? Okay, well, let's try and use a bit of what we know. So very, very, very roughly, what does optional look like? It's a class template. It has a Boolean, which says whether it's active or not. It has some storage, where it stores the value, where it may or may not actually exist. And it has this function called value. If it's active, it'll perform some kind of cast and give you a t ampersand. And if it's not active, it throws. Right? Hopefully everyone finds this like reasonably uncontroversial for the purposes of this slide. All right. Okay, so here's the code. So let's pretend some inlining happens. Most of these functions are very short, right? They're going to get inlined. Okay, well, you know, the Boolean check on an optional is basically just checking a Boolean flag. So that gets inlined. So now our first branch is if x dot, you know, inactive. And then internally, remember the other function, right? What did it do? It said, well, if x dot inactive, then do this thing. Otherwise, throw. So there's, you know, this once you imagine one step of inlining, the optimization is very obvious, right? It just stares you in the face. It's like, well, you can only even enter this branch if the predicate is true. So when a compiler is doing optimizations, whenever it's in a branch, you can always say in the context of that block that the predicate is true. Now, sometimes this is useless if the predicate is something complicated that involves evaluating a function that may have side effects. The compiler can't even reuse the value of the function anyway. But when it's something simple, it can be very useful. So in this case, the compiler just knows internally everywhere in here x.mActive is true. So when it comes across a second repeated branch, obviously it just eliminates them. And all of this stuff goes away, and you just end up with a single branch. Okay, so I'm going to move into the sort of last section of my talk, which is actually like things you can write and how you write them to help the compiler. Are there any questions up till now, by the way? This would be a natural point to ask.
You mentioned before that you don't worry about multi-threading, right?
I'm not worrying about multi-threading. Doesn't mean you should.
No. So in the previous slide, the compiler knows that there is no multi-thread to change the reference of it.
Don't have a memory variable or your phone or something, so you can assume.
Yeah, I mean, generally speaking, anything that's not marked as atomic is free for all. Yeah. Okay. Any other questions? No. Okay. Oh. Yeah. No. Okay, so helping the compiler. So this is like cute little construct that I call with bool. Before I talked about the fact that I talked about a loop pullout, right? The idea that you could have a branch inside a loop and the compiler could pull it outside the loop. So it turns out that this is not a very robust optimization. And I actually want to talk for a second about why it's not robust, because the compiler has very good reasons for it. So now let's imagine that there's a lot of code here, okay? And imagine there's a lot of code after. So what will happen if the compiler does a pullout of this branch, right? It does if B, then do this for loop, otherwise do this other for loop. What's the compiler going to have to do? They have to duplicate the code, right? And this is an example of like runtime information. Actually, sorry, this is an example of what do you care about. So you may care so much about this loop and about this branch that you're like, yeah, I don't care. Bloat the code, do it. Or, more realistically, a better example is that if this is a Boolean that eventually comes from the command line, I may only ever run either with B is true or B is false in any given program instantiation. In this case, the iCache costs of bloating this are minimal. Like, the binary will be bigger, but those other lines will never be executed. So they're going to have like minuscule impact on iCache additions, very close to zero. So compilers will not do this basically for you, unless the loop is really short. That's the bottom line, even at 03. And even with loops shorter than I expected, even a few lines. So how can we solve this problem? Let's say that we know the things that I just said. We really care about the performance. We know this. So how do we do this? Well, we use a template, right? With a template, we can stamp out a couple of different copies of the loop. So here's a version of Quax. This version, this overload actually just doesn't take a Boolean, right? It only takes a template parameter. And then it just writes the exact same code. And then here, you just basically pull, I don't know why. What's that? Yeah, I don't know why in my brain I always think of this as like lifting or pulling or something, but you take runtime information and you can always pay like a one-time cost to pull something back from runtime into compile time and then execute along different compile time branches. And actually in HFT, this trick is super, super, super common. Another example is like instead of a Boolean, imagine we have an enum that's called buy or sell. So you have some logic to place an order. You have to do a whole bunch of calculations, risk checks, calculate the price that you want. Okay, but you want to write the code in a natural way, but all the logic is basically reversed if it's a buy or a sell. So what are you going to do? Well, the answer is you're going to have buy or sell be like this something you're templated on, and you're only going to do the dispatch once, right? And in this case, you know that you need that code to run as quickly as possible as soon as you decide if you want to place a buy or a sell, right? The compiler doesn't know that. So this will work, right? And by the way, again, going back to another point, this whole optimization relies on this trick of if the compiler is not sure what optimization to do, it will always fall back to emitting assembly that is closer in spirit to your source code, right? So in the first version of this, I didn't have a template. I had a runtime if. So the compiler emits a runtime if because it's like, I'm not sure if this Boolean pullout is worth it. But then when you use templates, the compiler also will respect your decision to use templates. When you use templates, the compiler will basically never, it will only merge code from templates if the code is 100% identical and it costs you nothing. It will never, that I've seen, merge code if it means adding back runtime indirection. It could, it's allowed to, but it won't, which is really convenient for us users of the compiler.
You can use context for if there instead of the if.
You can use context for if, but do you think it will have any impact on the assembly?
No,
Okay.
just being more explicit about it.
Yeah, so the nice thing about context for if is that you will get a compilation error if it's not.
Right.
Yeah, that would be the main motivation to use it.
It's also just more visible for reading it,
Yeah,
which is like secondary.
sure, like a statement of intent. Yeah, that is true. So one thing so this is like kind of a nice trick is instead of doing this, you can actually pull this pattern out, extract it, and make it generic. So I just call it with bool. So it's real simple. It just, you pass it a callable and a Boolean, and it simply passes either true type or false type to that. The nice thing about true type or false type is that the type encodes whether it's a Boolean true or false, but they also have implicit conversions so they can be used in branches. So you can actually write very natural looking code with this. So here's my version of CoreCppIL written using with bool. So you can see I just do with bool b, and then it gets passed. This thing has to be auto, right? Because it's either true type or false type. It's one of two different types. This is a variadic lambda, so it's like a template function. So two versions of this lambda will actually get generated. They'll both get inlined, and basically we're able to force the compiler to do exactly the optimization that we want, with just a little massaging of C++ and template usage. No assembly writing required. Okay. My next example, generic pass by reference value. You only should use this trick if this is like really performance critical code. Otherwise, just let it go. So before in my example, I said pass by reference sucks. Here's all the reasons. And like, I'm sure some people in the audience were writing, well, when do you ever write const bool and anyway, right? I mean, no one does that. You're supposed to pass bool by value. That's true, but everyone who writes C++ actually writes const boolean, const int and const double and all the time. You do it every single time you write const tint, right? Because that's going to get called with a bool or a double or an int sooner or later, and now you're passing primitive types by reference, right? That sucks. So let's say you have something that you need to do really fast, and you have this problem that it's also generic. So how do you deal with this? Okay, so step one is we create a type trait. We call it pass by value. So what's a good set of, when should we decide to pass by value? So first of all, it has to be trivially copyable. Anything that's not trivially copyable, forget about it. It's never going to be worth it. Just pass it by reference. The second condition is something to do with size. There's no one right answer to this. I picked 16, which is 2 words on a modern architecture. This is like array view or string view. I think people usually are passing these by values. Seems to be the developing style. Bigger than that starts to get pretty borderline. Okay, and then you have your foo for not pass by value, and you have your foo for pass by value. Those of you who do a lot of metaprogramming already, this is probably like child's play. If you don't do a lot of metaprogramming, I really recommend looking at like the way in which I've written the enable if pairs, and just get in the habit of writing them similarly to that. If you do the type of enable if where you do like class equals enable if, this will not compile. So if you use enable if pairs a lot as pairs for like disjoint sets of functions, you have to do something like this. So you may as well just get in the habit of doing it all the time. That's the habit that I've gotten into. Yeah.
In this, you have to duplicate a function.
I'm getting to that. Okay. So now, great. So we know what the signature looks like, but how does the body look? This is like a really fun question. So are we going to write the value twice? Or sorry, we're going to write the function body twice? Well, no. We're going to. What do you do if you have to repeat code somewhere? We're programmers. We're going to factor it into a function, right? So I'm going to call foo impl.
the signature.
So what am I gonna? What's FWIMPL gonna look like? Well, I can just apply the same solution, right? I can just have FWIMPL, and then so we're making really good progress. So on the next slide, no, I'm just kidding. So obviously that's not gonna work, right? What's that?
המשתנה צריך להיות,
Template parameter?
הוא צריך להביא את עצמו בכמה תנאי.
Sorry, what are you suggesting in the
Make a
solution?
type alias for the right type of parameter that you want, and then use that in the function signature as the parameter.
Use type alias.
Using can be a template.
Okay.
You can switch between them.
Sure. But you will still have the same problem, right? Ultimately, you have to pass data, and you're selecting how it gets passed, but then you need to share the implementation of how that data is handled.
You can have a specialized type
A template specialization.
for the type.
For it itself. You can just select a forwarding reference and just.
But then you're back to references, right?
Remove reference.
Like remove reference and
It
things like
becomes
that.
whatever it was.
You can do a forwarding reference, but that's already a reference. But as soon as you do a forwarding reference, it's not passed by value anymore. So if that doesn't get inlined, you're SOL.
אותו טריק שיש כמו ל-remove reference, שאם אין reference הוא מחזיר, ואם יש אז מוריד אותו, אז באותה צורה אפשר להוסיף ולהוריד בהתאם לגודל.
You can, but
להכניס את זה לתוך סטרקט, את הפקודה המשמעותית של התנאי, לשים בתוך הפרמטר, במקום T.
I see what you're saying.
Will it optimize?
Huh? Will it optimize? That's a good question. Maybe it will. But here's how I did it. I mean, so I know everyone's like, "Oh man, you cheated! You actually, you didn't have like a really cool, clever C++ trick for it."
Portable.
Yeah, whatever. Just have you should have an inline macro by now, and MSVC also has some way of force inline, whatever it's
But
called.
I'm not doing the same things that.
That's not good, so. Thankfully, I don't write for MSVC, so.
Lucky you.
Yeah, but anyhow. But this works, and it allows you to share the implementation. And once you're passing, it is actually important that you choose const end here, because if you choose to pass by value and it's something very complicated and the copy constructor could have side effects and stuff like that, I mean, I'm not 100% sure how this will shake out. But passing by const reference is the safe choice, and then when you force it to inline, then all of the nice optimization analysis that I talked about before is going to work. Okay. Yeah. Okay, so let's sort of bring it back to the end of the sort saga. So, you know, the problem with the sorting is sort of very similar to a lot of the issues that I've already touched on. When you pass a function pointer to std sort, what happens is that, as we know, sort is templated, right? But the type, it's templated on the type of the comparator. So only one std sort gets generated for, let's say, vector iterators and function pointers with this signature, like double, dual, right? So it only generates one std sort. And this function, right now it's a function, not a function template anymore because it's instantiated. This function has to be valid for every single call to it as far as the compiler knows. And because that's true, it's not, I mean, now hopefully it seems obvious, right? It's not allowed to inline it, right? The only way it can inline it, and this is a more advanced technique I didn't like really get into, there's something called cloning. So all compilers can do this. GCC is especially aggressive in my experience, but it can actually decide to take a function and instead of inlining it, it can say, okay, I'm going to take this function and I'm going to make a clone of it. In other words, it's another whole copy of this function, but I'm not going to inline it. The usage of this is that I'm going to be able to assume that it's called with certain constants. So it could make a clone of std sort, function pointer comparator, that assumes that the value of the third argument is exactly this. Okay? But again, should you do cloning or not? I mean, obviously, as the name implies, cloning means code bloat. So compilers, again, when they're not sure, they tend to fall back to, well, I'm going to generate it the way it was written. And when you pass a function pointer, you're basically saying the way it was written is to not inline. So, inlining function pointers, it reminds me about what Mark Twain said about the weather. Everyone's talking about it. People aren't really doing it.
But it seems kind of backwards because it's not function pointer. You actually know it's like a literal value, right? I mean, the function is obviously known to compile type, the type and the signature, even the implementation.
Yeah.
In this example.
Everything.
And my comp is essentially a literal value. It's not
It is a
even a
literal
function pointer. It's a literal
But its type
function
is.
pointer, so it could do that cloning without a problem because it's like instantiating.
It could do the cloning without a problem, but it has to decide, like, did you want your code loaded or not? When you wrap it in a lambda, you're telling the compiler unambiguously. The lambda has unique type. I want a unique instantiation of std sort. Now the compiler will respect your wishes. So that's why in my
It's like
example
a judgment value.
for the compiler. Yes, but the compiler can't make judgment calls. So that's why they default to things as written. And that's also why function pointers, one of the reasons why it's very, very rare. Like all of this stuff taken together that I've talked about, it's very rare for function pointers to actually get inlined because when they're passed as template parameters, the type of the function pointer is not unique anyway. So the templating doesn't help at all. So when you have a normal function that takes something by function pointer, if it doesn't get inlined or cloned, which are both judgment calls for the compiler, it's not getting inlined. Like there's no way. It has one of those two things has to happen. Short of like LTO or if the function is declared static or an anonymous namespace, so it's internal linkage, but in the general case, it's not getting inlined. So the lambda is weird, right? Because the lambda adds code. So it's like, how can adding code possibly make this faster? It's just like another hoop to jump through, right? Well, the reason why is because the lambda forces a unique type for sort. The lambda gets inlined, and the lambda is hard-coded to call the function. So the compiler has no problem inlining the function into the lambda.
What about functors?
Functor is the same thing as a lambda function. We're supposed to call them function objects now. And it's the same thing. A lambda is basically the same thing as a function object of like unique, magically created type. So, yeah. Those get inlined too. Okay, so one thing that would be nice is instead of going through this agonizing, like roundabout way of forwarding the function into a lambda every time, wouldn't it be nice if you just do this automatically? And the answer is in C++ 17, you actually can. So how many people have seen this before, auto F? Some people have seen it. So this is nice because it lets you have a non-type template parameter of deduced type. Okay, so it's not a type template parameter. It's deducing F as a value. But F's type is also being deduced simultaneously. Okay, this is not possible prior to 17. You would have to deduce first class T, comma, T, little t, something like this.
Mm-hmm.
And people don't use them that often, but it's always good to remember that integers are not the only things you can template on by value. You can also template on the value of pointers, especially function pointers. It can be pretty useful. So this is what this looks like. All it is a function object with perfect forwards into F. That's it. And if you use this, this becomes that. So you have this weird situation where lifting your function pointer into a lambda is totally non-informative operation. It's actually really useful for the compiler and even your faster code.
So this works same as the lambda.
Yeah, exactly the same as the lambda. This is actually the basis for a proposal, not by me, from a while ago. It's called monostate function. As the name implies, there's no actual state of the function object. It's the information that it carries is just that it's type, basically. The type is the useful information. Okay, so conclusion. I really encourage you to avoid generalizations. A lot of people will say the compiler's smart, the compiler's dumb, the compiler's amazing, this. Like, just try to avoid useless generalizations. Compiler's very, very smart in some ways. It's not dumb, but it's intrinsically limited in others by information that it doesn't have, by things it doesn't know about what you want. So try to understand where you can add value to the compiler and how you should. As a kind of like final story for people who follow chess probably already know this, but people know how computers can be humans at chess, but a lot of people don't know that actually there are tournaments where humans use computers and they play chess together. And actually, a human playing with a computer is much, much, much stronger than either a human or a computer by itself. So the humans make the moves, but they're allowed to use computers as much as they want. So they have these tournaments. So I think it's kind of the same thing here. I mean, you could just handwrite assembly, and you could just let the compiler optimize, having no idea what's going on. But I think that if you want to write the fastest possible code as quickly as possible, you want to understand how the compiler works and learn to help the compiler and work with it. So thank you for my talk, for listening to my talk, and any questions?
You just mentioned briefly, but you're saying that C-style static functions, file scope static functions are better opportunities for the compiler to optimize?
C-scope. Why do you call them C-scope?
C-style file scope. Static in the file scope. Because it's a single compilation unit?
I mean, yeah, maybe.
Yeah, I don't like the conclusion either, but that's what I'm getting at.
Well, first of all, there's nothing C-style. I mean, I don't know. I don't think of them as C-style anyway. They're just a translation unit. Huh? Anonymous namespaces is the same thing. Oh, I mean, they're marginally better. I don't think it really makes any difference. I mean, it's risky for the compiler to conclude that it's okay to inline because it's not used anywhere else, because the compiler doesn't actually know if it's in a header file or in a CPP file, really. At least I don't think any compiler is using that as a heuristic. So if you have a very long function that's defined in a header file, you decide to inline it because you're like, great, it's static, no one else knows about it. And then the other 50 translation units that include that header file also all use the function, also all get it inlined.
But it's a
No, it's in a header file, it's the same function.
It's a different function. It's considered a different function because it's static.
It's internal linking.
Unless you use the Unity build where you include your CPP files and
yeah. That's another story. I mean,
may probably put them all together.
No, it can't.
No, it cannot.
If you have a static variable inside this static variable.
Well, I mean,
For example,
it can find out or
You
not.
can do it.
I mean,
You can include a CPP file.
Yeah, Unity build.
sure. I mean, is it? I mean, it will still merge the code if it finds out that it's identical, right? Like, regardless of what the standard says, if you have an inline static function that's defined in a header file, you know, if you look at your final binary, if you call this, if it's too long to get inlined, the final binary will only have one copy of the function, regardless.
Unless you have a static variable inside this function has to have different copies.
If you have a static variable, then yes, but otherwise, it will not. Yeah, not really. To answer your question, no. And if you want to, you seem to associate with like C-style stuff. So if it's any consolation, like one of the major takeaways from this talk should be that C-style APIs are much worse for optimization. You know, like QSort, for instance, was like, you know. Actually, here's a fun bit of trivia. Does anyone know a second reason why QSort is standard slower than STD sort? The inlining is actually not the only reason. There's two reasons, which also kind of come back to. So the second reason why is because QSort doesn't even know the sizes of the types that it's sorting, right? That's passed as a runtime parameter. So that means that whenever QSort decides to do a swap, it literally has some runtime variable there that's like, okay, 4 bytes. So then it has to like copy 4 bytes, like in a for loop where it counts up to 4 for every byte. So think about how insanely slow that is when you have like a double, which is one register anyway. Unless it clones. Yeah, but it's unlikely to happen because QSort's defined in a CBP file, right? So when you're using it, so it's not likely to be defined. But anyway, yeah. Any other questions for the talk?
Thank you very much.